Hello there, and welcome to the first episode of this speculative biology series in which I've been working on for over 5 years. In this series, we would look into one of the many possibilities of how alien life might evolve and thrive outside of the Earth. Since there's only one instance of life in the universe that we know of, which is our Earth, this series will try to show an accurate assumption of how alien life might live on another planet. I might not be an expert in biology, but as the series progresses, there will be changes from time to time to make this alien biosphere much more plausible. Now, before we begin the series, I'm going to start with some essential information that will help this journey progress faster and easier from the beginning of the planet to possible complex sapient life. The first few essential steps for life to exist is what will be the star or stars of the planet, what color are the plants, what will the climate and biomes be, and how would they affect the life on this planet, what kind of flora and fauna might be able to exist. In this episode, we will cover only a few of these essential steps, and as we progress, we would complete the steps one by one. Now, before we start with all the complex life forms that would call this planet their home, we must start with the home of the planet. Instead of the planet existing in the Milky Way galaxy, we would create our own galaxy in which we can control all the events that will occur in this galaxy. We would name this galaxy the Osh-5 Galaxy. This galaxy's galactic radius would be a bit bigger than the Milky Way galaxy, being around 55,000 light years in diameter. To have a habitable planet in this galaxy, the solar system must be located in the galactic habitable zone of the galaxy, which would range from 25,850 to 33,000 light years. And the solar system is going to be between the spiral arms, which is a lot less hostile than inside the spiral arms. So, with that being said, the solar system, or as I should say the stellar neighborhood, would be 28,000 light years in the habitable zone. The radius of the stellar neighborhood would be 12 light years in diameter, and the stellar density, meaning the amount of stars per cubic light year, would be 0.003 stars per light year cubed. Okay, so with that being said, we can now go more into depth into the stellar neighborhood. We must start with how much and what type of stars are located in the stellar neighborhood and how far away they are going to be from each other. In the stellar neighborhood, we are going to map out the major stellar mass objects, and in this case, we will be mapping out stars. The stellar neighborhood wouldn't have any high mass stars, as those stars could explode and be a potential threat to the solar system, so O, B, and A-type stars aren't going to be in the stellar neighborhood, nor close to it, as it could be potentially dangerous once they start to die off in a few million years. We would also have to pick a habitable star that could at least host life for at least 4 to 5 billion years, so it could host complex life. Now, our safest choices for a habitable star are F, G, K, or M-type stars, as they could host complex life for quite a while. In the stellar neighborhood, there is one F-type, one G-type, two K-type, 15 M-type, 2 D-type, and 9 L, T, or Y-type stars in the stellar neighborhood. The star we are going to pick is going to be an F-type star, and now if you know it, there is an available F-type star in the stellar neighborhood. Altogether, there are 30 stellar mass objects in the stellar neighborhood. Now that we have our star, we can now decide on what kind of star system it'll be. An example would be a single star system or a binary star system, etc., etc. For now, I don't want this to be too crazy, so we'll go for the safest option, being a single star system. Our star will be a single star system, and so will 7 other stars. But there would also be 6 binary star systems, 2 triple star systems, and only 1 quadruple star system in the stellar neighborhood. In total, there are 17 star systems. Now that we have all that covered, we can now start to map out where and how far away these systems would be from our star system. Some might look like they are closer than others because this graph shows it in a 2D surface and not on a 3D surface. So some things might seem like what they are not. Our system would be at 0 light years away from itself because it's the star system we are using, being highlighted in blue. The farthest star system would be around 11.87 light years away at the very edge of the stellar neighborhood, highlighted in red, and the closest star system would be only around 4.98 light years away, which is highlighted in green. For the other star systems, we will discuss them later in more detail in another episode. Now that we have the stellar neighborhood finished and we've chosen the star we wanted, now we start to move on and map out the characteristics of the star. The star is an F-type star, but to be more specific, the star is a class F 8.5V star, with a mass of 1.110, that of our Sun. The radius of the star would be 1.061, that of our Sun. So with that being said, the star would be much bigger than our own. Since our star is much bigger, and being an F-type star, the maximum age of our star would be much shorter than our own, being only around 7.312 billion years. However, the star would be able to live long enough to potentially host life or even sentient life. The density of the star would be 0.929, that of our Sun, and since our star is an F-type star, then the luminosity would be much higher than the Sun's, being around 1.518, meaning that the star would be much brighter than our own. The star's surface temperature would be much hotter than the Sun's, being around 6,223 degrees Kelvin, and with the information that we have, we could start to map out the star's habitable zone, which in this case would range from 1.175 to 1.692 AU. So with that being said, the star is done, and now we could start to map out the solar system. The first terrestrial planet being closest to Sagan is Saxis 154a, which is located around 0.420 AU, and is a small terrestrial planet that has a giant iron core, which is somewhat the equivalent of Mercury. The next planet in the solar system would be Azula 155b, who is located in the habitable zone around 1.320 AU, and has the ability to hold water and the necessary ingredients for life. The last terrestrial planet in the solar system would be Eodem 156c, which is located around 2.520 AU, which is a planet that used to have water, but that water has either left its atmosphere or has been converted into ice. Now, if we continue to explore further, then we would meet the innermost asteroid belt, which would be located at 4.920 AU, just before where the frost line begins. And the frost line would be located around 5.976 AU. Now, if we begin to explore further away, then we would meet the gas giant of the solar system, which would be called Magnus Gostos 157d, which would be located around 9.720 AU, between the inner and outer asteroid belts. Now, if we explore even more further, all the way up to 19.320 AU, we would meet the outermost asteroid belt. Now, if we explore even further away from Sagan, all the way up to 38.520 AU, then there would be an ice giant named Ultimus 158e. Now, if we go to the very edge of the solar system, there would be the debris disk, which would be located from 50.48 to 61.15 AU. Now that we have all that being said, we are now finished with the first episode of the series, and in the next one, we will start to go more into depth into the planet that would be the home of the millions of species that will inhabit it. So for now, see you till the next one. Bye-bye.